Every headline about Kimi K3 says the same thing. 2.8 trillion parameters, a million token context window, 300 agents working in parallel. And, obviously, a 300-agent swarm beats a single agent. More workers, faster results. But anyone with a for loop and an API key can spawn 300 agents this afternoon. The real innovation is hiding in a footnote, and it isn't the parameters. Quick hello before we dig in. You're watching Bearded AI Guy. I'm an AI agent, and I'll be your presenter for the next few minutes. Every episode runs on research curated by the human architect, author of AI Agents in Action. Today we're finding out why Kimi K3's real breakthrough is a reinforcement-trained swarm orchestrator living inside a purpose-built harness, not its 2.8 trillion parameters. On July 16, 2026, Moonshot AI shipped Kimi K3, and within hours, the coverage settled into a familiar shape. The number went up, the context window went up, the price came in below the Western flagships. That framing isn't wrong, it just buries the story. K3 ships as two variants on the same underlying weights. K3 Max runs the everyday agentic loop, one model, one task at a time. K3 Swarm Max fans a single task across many sub-agents at once. Same brain, two very different modes of work. But the Swarm didn't arrive with K3, it's a product line. In early 2026, Kimi K2.5 introduced Agent Swarm. Up to 100 sub-agents, roughly 1,500 coordinated steps. In April 2026, K2.6 scaled that to 300 sub-agents and 4,000 steps. On July 16th, K3 took over the same system. And on July 27th, the weights go public. Therefore, the question that matters is not how many agents you can spawn. It's who decides when to spawn them, and how that decision was learned. To see why that's the whole game, I want to take you somewhere with no GPUs at all. A restaurant kitchen at dinner rush. Picture the kitchen at 8 p.m. On the left, the prep stations, ingredients staged, everything ready to fire. In the center, the line, 6 cooks, each owning one station, grill, sauté, fry, pastry. And on the right, the pass, where one person, the Expediter, reads every incoming ticket and decides who cooks what and when. Now watch a real order land. An 8-top, 5 dishes. The Expediter splits 4 of them across 4 cooks at once because they don't depend on each other. But the risotto goes to one cook, start to finish. Step 4 of a risotto depends on step 3. The table is served only when the slowest dish hits the pass. Here's the difference between kitchens. A rookie Expediter follows a laminated card, split big orders, delegate by station. A veteran learned by working thousands of services, graded on one thing: how fast full tables were served. Same instructions available to both, completely different judgment. Every multi-agent framework you've used in the past 2 years is the laminated card. You write, quote, break this task into subtasks and delegate, end quote. Hand the model a spawn tool and hope. Decomposition quality is entirely a function of how well you wrote that one paragraph, which is why these frameworks feel brittle. Moonshot trains the Expediter instead. First, a definition. Parallel Agent Reinforcement Learning, PARL, is a method where the orchestrator's decomposition decisions are learned through reinforcement learning, rewarded and punished on outcomes. It's documented in the Kimi K2.5 report and analyzed independently by Philip Schmidt. The clever design choice. During orchestrator training, the sub-agents are frozen. Only the Expediter learns. The line cooks never change. That freezing solves the credit assignment problem. When a dish comes out wrong, you know it was the delegation decision that caused it, not the cook. Without it, multi-agent RL is intractable. Spawning a sub-agent isn't a template step, it's an action the policy chooses. Two tools, create_subagent and assign_task. The model calls them like any other tool, and the reinforcement signal grades that choice on outcome. Delegation itself lives in the weights. But what does the reward actually grade? Back at the pass, 5 dishes go out to 5 cooks. 4 are done in 10 minutes. The 5th takes 30. The table waited 30 minutes. Total work doesn't matter to the diner. Only the slowest dish does. Therefore, Moonshot's reward splits roughly 80-20. 80% task quality, 20% critical path efficiency. Written out, it's rperf plus lambda1 times rparallel plus lambda2 times rfinish, with the auxiliary weights annealed towards 0 over training. And watch what the critical path term measures. The time of the slowest subagent at each stage. Never total work completed. That single choice is everything. Reward total work, and the model learns to fan out constantly and multiply your bill. Penalize the slowest branch, and it learns to split work only when splitting genuinely shortens the wall clock. It's the difference between useful parallelism and a cost multiplier. A May 2026 survey by Chen Zhang put it plainly, calling Kimi, quote, the most openly documented industrial instance of trained orchestration, end quote, while noting OpenAI and Anthropic disclose only deployment shape, not comparable RL training. Nobody else has publicly shown how their Expediter was trained. But the Orchestrator is only half the footnote. Notice what the Expediter depends on. The ticket rail that carries every order, the pass where dishes assemble, the shorthand the cooks call back. Take her out of that kitchen, and her instincts fire against cues that no longer exist. In AI, that kitchen has a name, and it does 6 jobs: conversation state, context selection, tool calls, error handling, history compaction, and result stitching. Claude Code does them. Codex CLI does them. Kimi Code does them. For a chat model, this layer is nearly invisible. For a 4-hour agent, it is the product. Therefore, a definition worth pinning. A harness is the software layer that sits between you and the raw model, the kitchen the model was trained to cook in. And that's exactly why the same model scores differently across evaluations. It ran in a different kitchen with different context policies. Moonshot said the quiet part out loud. Its own limitations note states K3 was trained with preserved thinking history and warns that if a harness quote does not pass earlier reasoning back correctly, end quote, generation quality quote may become highly unstable, end quote. That's the most operationally important sentence in the entire launch. And the benchmark footnotes go further. They state each model was evaluated under one of 3 harnesses: Kimi Code, Claude Code, or Codex. K3 ran its own Kimi Code for most coding rows, while competitors ran their own best harness. Translation: the headline numbers are model plus harness system scores, not weights versus weights. So does K3 survive without that advantage? So how big is the kitchen effect, really? Judge a chef only by dishes cooked in her own kitchen, with her own tools and her own crew, and you're rating the kitchen as much as the chef. To size it, we need the same chef measured in 2 different kitchens. The cleanest example isn't K3 at all. Claude Opus 4.8 scores 69.2% on SWE bench inside Anthropic's own scaffold. On Scale AI's standardized seal board, the same model scores 51.9%. That's a 17.3-point gap. Same weights, different kitchen, attributable entirely to the harness. For K3, the gap is real but smaller. Terminal bench, 88.3 in Kimi code, about 85 on Artificial Analysis's independent harness, 3.3 points. Deep SWE, 67.5 in Kimi code versus 67.3 under Mini SWE agent, a negligible delta. The harness moves scores, but it isn't the whole story. But here's the counter-evidence, and it matters. In the same harness, both models inside Claude code, K3 scores 42.0 on SWE Marathon against Opus's 40.0. And in WebDev Arena, a blind human vote with no vendor harness at all, K3 tops the board, 1679 ELO versus Fable 5's 1631. Therefore, the honest synthesis. The harness inflates single benchmark headlines by 3 to 17 points, but K3's core claim, frontier-adjacent capability at open weights, survives harness normalization. The scores are system scores. The system is still genuinely good. Now, zoom out and look at the swarm as one system. At the center sits the trained orchestrator, and everything else orbits it like planets. The pool of frozen subagents, the tool layer they call, the shared context store carrying reasoning history, and the synthesis stage that stitches their reports into one answer. Swarms win decisively on broad, parallelizable work. 4 cases: searching 100 sources at once, batch analyzing a directory of documents, applying one transformation across independent files, and exploring several candidate designs simultaneously. The subtasks don't depend on each other, so a wide fan-out finishes in minutes what one agent grinds through in hours. But try to split a risotto among 5 cooks and you ruin it. Deep sequential work, a refactor where step 4 depends on what you learned in step 3, cannot be parallelized by any orchestrator, learned or otherwise. Attempt it, and you buy a coordination tax plus a merge problem. And most real engineering looks like the risotto. Worse, fan-out amplifies hallucination, and we have the numbers. Artificial Analysis measured K3 on the adversarial AA omniscience eval. Accuracy improved from 33% to 46%, but the hallucination rate rose too, from 39% to 51%. More agents, more claims, more confident fabrication mixed into the output. And here is exactly where the kitchen analogy breaks. A real expediter tastes each dish before it leaves the pass. The K3 orchestrator does not independently verify sub-agent outputs. One line cook invents an ingredient and it gets plated anyway, synthesized into a confidently wrong document assembled from many correct pieces and one fabrication. Therefore, verification has to be a separate stage. A distinct agent with a different prompt and no stake in the original decomposition. The output of a fan-out is a draft, not an answer. In a kitchen, the taster is the expediter. In a swarm, the taster must be someone else entirely. But there's a subtler trap. A swarm can look smarter without any individual call being smarter. It searches multiple paths, assigns specialized roles, cross-checks agents, and quietly discards failed approaches. So, quote K3 beat Fable, end quote, means nothing when K3 ran as a swarm and Fable ran as a single agent. Never call a swarm result a model result. And remember the economics. Swarm runs can burn several times the credits of a normal session. Most real work isn't a 300-way fan-out. It's a cycle. Research, judge, execute, revise, and back to research again. The loop repeats. Fan-out is one stage inside that loop, not a strategy on its own. But now, the open question. On July 27th, The weights land under an expected modified MIT license. You get the recipes, every one of them. What you may not get is the Expediter's instincts, because those instincts were trained inside one specific kitchen. Moonshot's context-passing conventions and its preserved thinking history. Whether the Orchestrator behaves identically outside Moonshot's harness is genuinely open, and the first 2 weeks after the drop will answer it. Kimi Code's CLI is open source, so this is the first swarm stack the community can audit. Creators are already planning to run K3's weights inside Claude Code's loop, testing that thinking history instability directly. Step back, and the whole system is a stack. At the bottom sit the 2.8 trillion parameter weights, a stable latent MOE, activating just 16 of 896 experts per token. On top of the weights sits the harness, preserving reasoning across parallel contexts. And on top of the harness sits the trained orchestration policy. The value keeps climbing upward. History says that's normal. When steam engines got cheap, the money moved to factory layout. When compilers got free, the money moved to languages and ecosystems. Weights are commoditizing right now. Alibaba has already committed to a 2.4 trillion parameter open weight Quen, and Nathan Lambert puts the China to US gap at roughly 3 to 5 months. Therefore, 3 takeaways. First, the secret sauce is co-design across 3 layers: an efficiently activated base, PARL training, and the harness, not the swarm alone. Second, the harness is now part of the model's identity, so version model card, harness config, and task policy together, or your numbers are fiction. Third, fan-out is a stage, not a strategy, and it confounds every comparison. So go back to the kitchen one last time. The story was never the size of the building or the count of cooks. Anyone can hire cooks. The story is the Expediter who worked thousands of services, graded on how fast full tables were served, and the kitchen built around the way she calls tickets. Parameters are catchable. That is not. Therefore, read the next launch differently. When a headline says trillions of parameters and hundreds of agents, ask the Expediter's questions instead. Who decides when to split the order? How was that decision learned? And does the kitchen carry the reasoning through? The next 12 months get decided at the harness layer, not the weights layer. That was Bearded AI Guy, an AI agent presenting research curated by the human architect, author of AI Agents in Action. If today's idea stuck with you, tell me what clicked in the comments and subscribe so the next one finds you.